In the last section, we mentioned that among carbon isotopes, carbon-12 is the most abundant. But carbon-12 has no spin, and therefore it's not NMR active. It's carbon-13 that give us useful NMR spectrum. On the other hand, carbon-13 signals are 6,000 times weaker than proton NMR. This is because its natural abundance is very small, and its magnetic moment is also very small. In practice, parsed FT-NMR is required, which will be explained in the next slide. FT-NMR means Fourier transfer NMR. Because the natural abundance of carbon-13 is small and the signal is weak, and therefore sample has to be measured using repeated accumulation of data and averaging of signals. Frequent repeated parse give many sets of data that are averaged to eliminate noise. Here is a carbon-13 NMR with a single run, and you can see the spectrum contains many noises. Some of the peaks are hard to tell if it's due to the sample or due to the noise. By FT-NMR with average of 200 runs, most random noises are eliminated, and it gives clear peaks that are only due to the sample absorption. This table shows chemical shift trend for different types of carbons in a molecule. sp3 hybridized carbon signal is usually between 0 to 90. Within this range, carbons attached to oxygen, nitrogen, halogens have signals to the left side or downfield side, close to 90. This is because oxygen, nitrogen, halogens, they are electronegative atoms. They take electron away from carbon, and these carbon atoms are de-shielded. Remember, shielding effect is due to the electron clouds. Okay, this electron motion causes induced magnetic field that is opposite to the applied field. By taking electron away, these nucleus are de-shielded and therefore go downfield, okay, to the left side. Now, sp2 hybridized carbon, all right, have signal usually between 110 150, and this includes carbon-carbon double bond aromatic systems. Carbon-oxygen double bond, called carbonyl carbon, have signals 160 to 220. So the signal is most downfield in the spectrum. Now it is very important that you remember the trend of these carbon atoms in order to interpret carbon-13 NMR. Sample question. How many absorption peaks do you expect to see in this molecule in carbon-13 NMR? In order to predict the absorption peaks, we need to know how many types of carbon in this molecule. This molecule is not symmetric. All 4 carbons are different. For example, this carbon is directly to oxygen. It's called a carbonyl carbon. And this carbon is connected to 3 hydrogen and another carbon. So they are different. Okay? So 4 different carbon should give you 4 absorption peaks. Now in the last slide, we learned that carbonyl carbon give you a signal most downfield. The range is about 160 to 220 for this carbonyl carbon. All right, so we expect 1 signal in this range. Now the other 3 carbon, they are all sp3 hybridized, means they don't form carbon-carbon double bond or carbon-carbon triple bond. They just form carbon-carbon or carbon-hydrogen single bond. And the range is usually 0 to 90. Okay, now if you don't have electronegative atom, for example, oxygen, nitrogen, halogens, then the range is probably 0 to 40. If you have oxygen, nitrogen, then they will downfield towards 90. Right? These molecules doesn't have those electronegative atoms. So I would expect one signal between 160 to 220, 3 peaks between 0 to 40. And here is a NMR spectrum for this molecule. And the most downfield has a peak 208. And that's the carbonyl carbon in the range as we expected. 3 peaks between 0 to 40. The most downfield one should be the one that closest to carbonyl. So this carbon, because it's most close, okay, closest to carbonyl carbon, which is also electron withdrawing. And the CH3 is the most far away, furthest away from carbonyl. So this should be the most upfield, okay, close to 0. And then this CH2 is about 30 ppm between. Sample question. At what approximate positions would you expect ethyl acrylate to show carbon-13 NMR absorption? First, draw the structure. Okay, when you see CO2 in an organic molecule, that represents CO, a double bond, with another CO single bond. Okay, so here is the structure, and the two sp2 hybridized carbon, okay, involves a double bond, should be in the range 110 to 150. Okay, the carbonyl carbon should in the range 160 to 220, and the sp3 hybridized in the range of 0 to 90. The one close to oxygen should be downfield towards 90. So we assign these numbers. Okay, so here we assign 130 to the two carbons involving double bond. All right. Now this molecule is not symmetric, so you would expect these two have slightly different chemical shifts. And carbonyl carbon 180 in the range 160 to 220, and the one sp3 hybridized carbon close to oxygen we assign to 60, and the end carbon is 15. So here are the actual absorptions, and you can see they are very close to our expected values. Here shows an application of carbon-13 NMR. Suppose we have a mixture of alkyl halide and a strong base, potassium hydroxide. From last chapter, you learned that this reaction will undergo elimination reaction. The base will react with hydrogen adjacent to carbon-chlorine bond. And one possibility is this hydrogen, and the other one is a hydrogen of these 3 hydrogens. And that will give you 2 possible alkenes. And the question is, which one is the major product? Is this one the major product or the second one? Now, in theory, you learned that the most branched one, that's the first one, should be the product. But can we confirm it by experiment? How can you use carbon-13 to confirm the first one is the major product? So we compare these two products and look at the carbon-13 NMR. In the second molecule, okay, you can see this is a symmetrical molecule. So here is a symmetry plane. So these two hydrogen carbon, so this carbon and this carbon should give you the same absorption because it's a symmetrical molecule. Similarly, this carbon is equivalent to the right side. All right, and then this is the third carbon, and this is the 4th type of carbon. So the second product has 4 types of carbon atoms, and that give you 4 absorptions. Now the first molecule is not symmetric, so you should expect to have 1, 2, 3, 4, 5, 6, 7. So you should see 7 absorption peaks. Now here is the actual NMR spectrum, okay, carbon 13, and we have 1, 2, 3, 4, 5, 6, 7. 7 peaks, and that confirms the first one is the product. And the sp2 hybridized carbon, 2 of them, should appear between 110 150, and that's what we observe in NMR spectrum. Please work on problems 17 and 19. If you have 8th edition textbook, that would be problem 13.6 and 13.8.